My name is Subin Kim, and I'm a third-year PhD student at KAIST in South Korea. And now I'm on research scientist intern at Adobe Firefly from March to September. So I'm in San Jose for a couple of months. And yeah, briefly, my research focus is on controlling diffusion models for higher dimensional synthesis at inference time. So today I'm gonna talk about my recent two papers that focus on higher dimensional synthesis, especially for feature data. So if you have any questions, feel free to interrupt me and you can leave the question at chat. Yeah. So yeah, today I'm gonna talk about the basic concepts of diffusion models and then move on to other papers, which the first thing is consistent visual editing across various and complex visual modality. And lastly, I'm going to talk about the long video generation with multi-event dynamics. Yeah, so let's start with the basic concept of diffusion models. So yeah, what is diffusion model? Diffusion model is one of a popular framework in generative modeling. So, which is it mimics the real data distribution by following this. So, a diffusion process gradually destroys unobserved data point X over time T by mixing data with Gaussian noise. So it assumes that real data comes from the Gaussian distribution, and it divides the process into timestep T. And at the training time, it adds the noise to the real image, and then it denoises the image during training. And then finally, at inference time, it starts from the Gaussian noise, and it removed the introduced it removed the predicted Gaussian noise for each time step, and at the final step, it gets the good synthesized data. So this is not limited to any vision or like visual data, but it could be applied to any modalities if we can have a plenty of data and we can train the model with that data. Yeah, but the most notable area of diffusion success is text to image generation. So then what makes diffusion models successful compared to other generative models? Why people focus more on diffusion model? Because arguably the framework is very simple and it works well, but it requires high quality large pair data and high computational resources. So usually people like you might know that if you just give some prompt to ChatGPT or like more LLMs, then it can generate the very high quality data. But to enable that, it must be accompanied by high quality large pair data sets, such as the text prompt for this image and the high quality image. And there should be a lot of pair data to train the model. And also, it requires high computational resources to train the model. But when applied this framework for more higher dimensional synthesis like videos or 3D scenes or whatever, the data becomes more scarce. So to obtain high quality data compared to image, it is much difficult to collecting high quality data and also it requires more computational resources to deal with more high dimensional data. So my work usually focuses on how to adapt the existing models without any training to expand the capability of existing models for more high dimensional data because it requires more data for training, but I'm focusing on how to adapt the capability without even training. Yeah. So yeah, and from now on, I will talk about my recent papers. The first one is consistent visual editing across various and complex visual modality. So I can briefly show some examples. Can you guys see the web browsers?
Yeah.
Yes.
I see. Thank you.
Okay.
So in this paper, we consider the following problem. This is the original Michelangelo's painting, but we can reimagine that this painting, the people in this painting are in galaxy. So we can also explore other things like Monet style and Van Gogh style, like that. So as shown here, this is the source image and this is the edited image to make the source image into Van Gogh style painting. We can also give more vivid color for the source image like that. Another example is to edit panorama image. So when we have a source image which is very long in horizon, how to make this into spring and fall. Also, we can apply other manipulation like summer and winter, and it shows some transition. And you can also change that into left part to Van Gogh style and the right part to Paul Gauguin style painting. So, and the other thing interesting is we can turn the video data into to satisfy the following prompt. So when you have the visual just original data, we can make it to spring or like midnight or sunny or autumn when the user gives just this prompt. You can easily give the prompt to manipulate the original data. So another application is 3D synthesis. So when you have a 3D asset like that visualize the 3D scene of the person's face, then we can turn that into we can reimagine him as a glowing, colorful, vaporwave 3D raw polygraphic object like that. And you can turn him into an anime character and we can make him smile. So yeah, we achieved this without any training. We just utilize the text to image diffusion models that generate image diffusion, image data with just text prompt. But this is not trained for very high resolution images or video and 3D scene. So I'm going to talk about how we achieve that. So this paper, as I briefly show, it focuses on visual editing across complex visual modality. So yeah, recent text image diffusion models have demonstrated remarkable success in generating high quality and realistic and diverse images with the given text. So when we have this prompt, Alien Lab in KAIS, which is my lab, so it can generate following images, and also the other application is like control that when we have this like pose, then it can generate following images that follow these pose. And also we have a sketch image, then when the model is guided by this image, then it can generate the following images that very much similar to given sketch. So, and the other application is personalization. So rather than just instead of just generating random images with given prompt, we can personalize our model. So when we have our good images of for corgis, then we can make the diffusion models to know the concept of our input images. So we can make our corgi in Acropolis, or my corgi is swimming and sleeping, and my corgi is in a bucket, or my corgi in a doghouse. And other interesting application is insert pics to pics, which edit the given image. So when we have this toy, then we can turn it into a still from a Western style. Another thing is we can add firework to the sky. And this is all of the application that is very well known for text to image domain, including like image to image translation, controllable generation, and personalization. But then how to adapt these fires beyond 2D images? Because as I mentioned, this is possible with a bunch of paired high quality data. But in case of panorama image and video and 3D scene, it is very hard to collect the kinds of very large data, and also train from scratch for this domain is very computationally expensive. So our question is how to adapt the existing priors of text image diffusion models for these kinds of complex feature data. So here our insight is we can consider the complex feature data is a set of images which requires modality-specific consistency. So in case of panorama image, it is a set of images that requiring spatial consistency. And in case of video, it is a set of images that require temporal consistency. And the 3D scene is a set of images that require view consistency. Yeah, so but unfortunately, diffusion just a text image diffusion model don't have any capability to ensure consistency between the samples. It just generates the image with the given prompt, but it does not consider the consistency between a set of images. So to ensure the consistency between samples, we focus on other optimization-based approach. The prior work of SDS, which is for distillation sampling, it enables the knowledge distillation of diffusion models. So their core idea is, as I mentioned before, when we generate the image, it starts from Gaussian noise and it iteratively remove the noise from the Gaussian noise, which is just straightforward sampling, generative sampling. But this paper posed the generative sampling as an optimization problem. So it allows the optimization of arbitrary differentiable operator by minimizing density distillation load. So when you have a function G and the parameter data that generate the image X, and we can this SDS pose this generative sampling to the optimization problem, and this is the following equation. You don't need to see the detail in this equation, but you can see that it just considers just one sample. So as it has many freedom because it changed the generative sampling to optimization problem, but it considers just one sample. So in here, our paper, we consider some multiple samples to share their knowledge for inter-sample consistency. So addition here, we generalize this equation to like here. So in detail, we brought same version of Nissan, which iteratively transferred a set of particles to measure target distribution. But the major difference is, as shown here, it just considers one samples, but we can consider multiple samples. And during optimization, we let multiple samples to communicate to each other. So just the sample parameter update is affected by others when during sampling, during optimization process. So instead of just every sample goes to their one denoising optimization, every sample can communicate during optimization with our framework. So yeah, that's the basic concept. And by applying our method, we can edit the panorama images. So as shown here, when you have a search image, then the easiest way is just divide the long image into just patchwise crop. Because just edit this very long image with just downsampling, then it might suffer from low quality. So we can just divide the long image into patches. But when you divide the patches and edit images for that part and then stitch again, then it shows very noticeable artifacts between like when stitching. The other thing is to let the overlapping patches and adapt and use the instruct fix which edit the image. But it does not follow a given prompt. It does not genuinely turn the given image into a Van Gogh style painting. But with our framework, we can make the source image into a Van Gogh style. Because we let multiple patches to communicate during optimization. But without our framework, the guidance by each patch is diluted by others, so it cannot follow the given prompt. So interestingly, without any training on very high dimensional data and without any pair data set on panorama image, we can just turn the panorama image into our with just text prompt, and this is based on just text image diffusion models. And the other application is video editing. So the left three are based on video editing work. But although our framework is versatile and does not even trained or not any component specific to video data, but it shows better performance compared to existing video models. It can
Tim,
easily, yeah.
yes, I've got some questions that
Oh yeah.
I wonder about here. I wanted to know that the framework that being used adopts a pre-trained diffusion model, right?
Yeah, exactly.
Okay. And should that mean that the pre-trained model has not been trained on this sort of high dimensional data, and so, but with the new framework, your technique allows this pre-trained model to start synthesizing on these high dimensional images and sort of videos.
Mm-hmm.
So that's what happens. Also, I wanted you to clear about the sampling process in sort of like during inference.
Mm-hmm.
Like, how can someone reason about it if we reason about sampling in sort of like other sorts of data? It could be like protein sequences, or even if it is images themselves.
Mm-hmm.
How is this sampling happening during inference time?
Like, what if the domain is changed to like 14 or something else?
No, like for the case of proteins, it could be like you trying to predict maybe new amino acids or protein sequences on a certain existing protein, something like that. But if we take the example of the images,
Mm-hmm.
we the sampling. I'm trying to understand the sampling process during inference. That's where I'm trying to, because in training maybe it is understandable during training, but is it the same anyway during inference, like the same way it happens during training?
Oh,
Because yes, because this is a pre-trained model, so I'm just trying to understand what happens during inference.
Yeah, so your question is, yeah. During training, the purpose of this diffusion model is to translate the given image into the other one following the prompt. So when you have an image of just a bird, then we just train that bird and the spring version of the bird, and then train the diffusion model to make this bird to like spring version of this bird. And this is the instruct pick which just edit the given image. But it just only applicable to just very small resolution images. So in this work, we adapt that to panorama image and video and 3D scenes. And then to achieve that, rather than just utilizing sampling, it focuses on optimization problem. So I'll go more detail. So as shown here, the data X becomes the actual data that we want to generate. So we can consider that when you have video samples of this stock, then the visual data of this stock might be X. And then we optimize the theta. And then this theta is optimized by the diffusion loss. But this is a little bit different from just sampling, that we just remove the introduced noise during timestep denoising.
Okay.
Yeah.
Okay. Then this process of distillation sampling, for when I think about distillation, in the classical sense, when some knowledge filtrates into another sort of like entity, such that the model lands in sort of teaching, that sort of way.
Oh
My
yeah.
question is about this distillation loss, the minimizing it. Um, and in still my mind is still about inference. I don't know whether there is training that happens within, like, to the model itself, but uh, I'm seeking for a clear sort of understanding about the this distillation loss during inference. If you can give more details about it.
Oh, I see. Yeah. We can obtain this diffusion equation by just using just original diffusion training loss, as you said. So I do not bring that exact equation for training diffusion model, but when you have training loss of diffusion model, and we want diffusion model to distill that pre-trained prior for optimizing other new samples. So to obtain this equation, we just differentiate the existing diffusion loss with respect to generator parameter theta. So when we have diffusion loss and we want to optimize parameter X, and we differentiate the diffusion loss with respect to generator parameters theta. And it gives the following equation like that.
Okay, makes sense.
So yeah.
Okay,
So
thank you.
we can obtain that by just differentiate the original diffusion loss with respect to generator parameters theta.
Okay, that's all right.
Oh yeah. So yeah. So and this is the theoretical detail, but I'm not going into very detail, but the important thing is we consider multiple samples and generalize with the optimization problem. So we let multiple samples to communicate each other when optimization. So yeah, this is another example. So when you have a source 3D scene, then we can make him as a glowing colorful graphic object, and also we can also make him smile. But without our method, it does not give very detailed image of him. It loses the detail of original image, because in 3D scenes, when you edit 3D scenes, there are multiple view of the 3D scenes. But to preserve detail, the edited part of each view should be same. But if the same part becomes different when after editing, then it loses the detail. So that's why our method shows the clear shape of him as a glowing colorful vapor wave, but the others are not. Yeah. So in summary, we introduced collaborative score distillation for consistent visual editing. And our question here is how to extend the existing capability of text to diffusion models to manipulate high-dimensional visuals. So our insight is we interpret complex visuals as multiple samples with their modality-specific consistency and impose consistency between them. So instead of just optimizing one sample, during optimization problem, we impose consistency between multiple samples. So by doing so, beyond a single 2D image with fixed resolution, we can edit panorama image, video, and 3D scenes. Yep, and based on this work, I'm gonna introduce my recent work, which is long video generation with multi-band dynamics. So here are some teasers. So as shown here, anthropomorphic gorilla first strumming energetically with a pure expression, and then it grins widely as it plays a powerful leaf. And then it strumming its foot and wind back dramatically, like that. So from now on, I'm going to talk about the long video generation, especially with multi-band dynamics such as strumming, green widely, and stopping each foot and wind back. Followed by text image diffusion models.
I have a question, please. Thank you for the work I presented so far. I appreciate the presentation. It is all detailed. My background is in statistics and biostatistics, so more of medicine. So with the modeling you are working on or you've worked on during your PhD, how applicable are they to the field of medicine? Do you have any chance that that can be applied into medicine?
Medicine? I don't know much about the medicine, but in case of medicine, people are using diffusion models to generate, like, for medicine or some other chemical structures, right? Like protein structures.
Yes.
Yeah. So yeah.
So are you looking at improving this to fit the context of medicine, being that there's still a bigger gap in visualization? Are you looking at like improving maybe after your PhD, postdoc or something, building on this to fit the context of medicine? You get my question, please?
Yeah, so your question is, we can apply this one for medicine, right?
Yes. How applicable is it? Like, are you looking at yourself applying it to medicine at one point?
I do not explore my work for medicine, but it could be it easily applied to medicine if there is a diffusion models for medicine.
Oh, okay. Okay, thank you.
Yeah, like protein structures or something else. So when we have a text or some other condition to protein structure models, for example, then we wanted to generate a bunch of protein structures which is very similar, then we can use our previous framework. And also when we want to, I don't know much about the detail of the protein, but if the protein can generate like these long sequences and we want to generate much longer sequences, but they are very they have many correlations, then we can use this framework to generate very long sequence of protein.
Oh, okay. Thank you.
Yeah. And, yeah. So yeah. As shown here, the text video diffusion models are very amazing, which is very like real data. And this is other example. Yeah. So I believe one day text to video diffusion models could be widely used for content creation. But here is the challenge. When we have very long text prompt, for example, an anthropomorphic gorilla is first playing with the fierce expression and strong sentiment each foot and lean back, and generate this text prompt and use this text prompt to generate video. But there are two major problems. The first thing is they are limited to very short video. And the second thing is they often show a single event. In case of this text prompt, it consists of like broadly 4 different events of various expressions, terms, and some is food and reading back, but it just not the current diffusion model just generates a single event. But to make diffusion models for content creation, it should be able to generate very long videos and with multi-event dynamics. So then, how to extend text-to-video diffusion models for multi-event long videos? One way is to train the model with the very long data, but we do not have very long data, and it requires much more computation time and training resources. So another simple way is to extend the diffusion models at inference time, and and also we could achieve that by these short video clips to longer video clips. But of course, direct stitching does not ensure the smooth transition between clips. So the basic way and straightforward way is to divide the long video into overlapping short video chunk, and then we average the overlapping part during generation, not at the final samples. So when you have a very long video, we divide that long video into overlapping video, short video chunk, and then conduct diffusion forward for each video chunk, which is guided by each distinct prompt, and then average the overlapped regions to ensure smooth output. And then we repeat from 1 to 3 during our sampling. So by doing so, we can obtain these kinds of long videos. First, a handsome young man takes a slow sip, and then a beautiful young lady sits beside him. But the problem is, it is long video, right? And it shows very smooth transition, describing multiple events. But it shows unnatural and other changes. The man abruptly translate into a woman. This is not the video that we want to generate. So why this happen? Because while temporal denoising with just overlapping video chunk works and it is effective for smoothing, but it does not let the long distance video chunk to communicate. The first chunk and the last chunk are not communicating directly and they lack of global synchronization. Just overlapping parts are smoothed out, so they show the smooth transition from the first chunk to the last chunk, but they do not communicate to each other. So that's why that's why the generated video shows unnatural transition. So the other idea is conduct temporal co-denoising with our previous framework CSD. So CSD was designed to accommodate global synchronization of multiple samples synchronous consistency. Then what happens when you apply CSD to long video generation? Yeah, it seems like a handsome young man takes a slow step, and the last video, and it shows a young lady, maybe this one, but it shows very severe noise-like artifacts, while it shows global continuity in semantics. This is because CSD is designed for editing, not pure generation. So then what happens for just overlapping and CSD? When we visualize the feature trajectory during sampling, we found that from Gaussian noise, when we just denoise the whole chunk with just temporal co-denoising of averaging, it shows the passes gets divergent because the average chunk do not communicate with the very long distance chunk. So that's why it shows the very divergent denoising passes. But with our previous work CSD, the sample space easily collapsed into the similar ones. So it shows very noise-like artifacts. So in this paper, we focus on how to strike a balance between divergent and collapsed passes to make balanced denoising passes. So in a high level, our approach is to combine two samplings of previous one to capture both global coherency and local smoothness. We couple two samplings into a unified framework. So of course, pair combination misaligns certain using trajectories. So to address this, we introduced some kinds of techniques to unify them into a single new inference framework. So by doing so, we strike a balance between divergent and collapsed noising passes in this blue dot. And the last one is our example.
Kim, I had a question about.
Mm-hmm.
Yeah, so you said somewhere that there is the strategy here is to chunk up these long videos into small chunks.
Yeah.
And my question is, probably I missed it. Maybe you hinted on it. Do these small chunks, each chunk is fed into the model with the respective text prompt, or you have a single
exactly.
prompt?
Multiple prompt for each chunk, and each chunk is guided by its distinct prompt.
Okay.
Yeah, that's right. So in this example, we just want to generate the 2 times longer video, and then in case of the when we can then when this is the 2 times longer video, then we can divide that into 4 overlapping chunks, and then guide the first 2 chunks with the prompt of the a handsome young man takes a slow step, and the last 2 chunks with the prompt of a beautiful young lady sits beside him to make a multi-event.
Okay. That's great.
Yeah, so by doing so, we can balance between collapsed and divergent denoising passes. This is the basic of our framework. And by doing so, compared to other works, our framework shows strong.
So Kim, about the previous slide. So yes, the intermediate sort of video that is faded and like what would be the explanation here of such a result? The middle video, I would say. I don't know whether it is an intermediate result.
This is not the intermediate widget, it is the final widget, and I do not bring the intermediate features, but intermediate feature shows the partially denoised videos.
Okay, it's just like fascinating. I would love to know that middle. I don't know that it's a video, a picture of the man taking a cup of tea, but here it is faded, like you can barely even like understand unless you have clue about the final image that appears as the first here. So I was wondering whether it is an intermediate image or it is a final result. And if it is a final result, like why do we have such a result?
So your question is how to know that the final image would be like that?
Okay, maybe we need to you need to clarify that it's a video. I thought it's a video.
Yeah, it's a video.
So is it SynCoS, like the synchronized coupled sampling that is producing this middle video, the one in between? How does it come about? Mainly, that's what I love to know. You get my question?
Could you repeat again? I think I cannot get the point.
Okay,
Sorry.
the question I have is about on this very slide, the image in between of that is faded and low pixel, not the image but the video, because they are videos, but the middle video of faded, of a gentleman taking a cup of tea. And my question is it coming from the synchronized decoupled sampling when you adopt that strategy within the framework, or it's an intermediate, like sort of result generated as an intermediate result or intermediary that it will result into a final video? How does it come about? That's mainly what I'm asking.
Yeah, this is not the intermediate widget, and this is just the temporal co-denoising with overlapping, averaging, and this is the temporal co-denoising with CST, not the intermediate widget of our SynCoS framework.
Okay. All right.
And this visualize this is the intermediate visualization. So it might be a little bit confusing, but this is the final videos and this is the visualization of intermediate denoising passes to visualize that
okay.
this
That
video
makes
gets
sense.
divergent and this video gets collapsed. But although they are or starts from same initial point.
Okay, perfect. That makes more sense.
Yeah.
Okay.
So
thank you.
Yeah. No, I'm thinking. So when start from the same initial noise, when just use the temporal co-denoising with the DIM, it gets divergent because the first chunk and the last chunk do not communicate during sampling. And in case of CST, it gets very collapsed region. And in case of our video, we strike balance between divergent and collapsed region. So that's why I visualize this intermediate trajectory, and this is the final region. Yeah, so by doing so, our framework shows strong long-range temporal coherence. So when we have a global prompt that is applied to two distinct local prompts, which is an astronaut in a white spacesuit with reflective feature, and there are two local prompts to control the long video. And the first one is the astronaut works, and the second one is the astronaut stands still. So in case of previous work, it works at first time, but it translates into animal-like images, and it automatically shows the shape of the astronaut, which is not shown in previous frame. It changes very dramatically, which is not the natural transition. And in case of this work, it in case of intermediate frames, it shows some anime style. But compared to that, our framework shows smooth transition between local frames, and also we obtain long-range temporal consistency in semantic or content. Yep, so this is other example. The first, a camel in a snowy environment, and the first prompt is about the camel is running, and the second prompt is the camel stands still. And this video shows the camel is running and is start to stand still.
Kim, I don't know, there was a question in the chat. I don't know that you saw it. Someone was asking, on average, how many diffusion models are used in the collaborative score distillation?
So I didn't see the chat.
Is wondering, during collaborative score distillation, how many models are used? And
how many models?
Even you? Yes.
Just one model.
Okay. I think that is answered.
Oh, sorry for missing the question. I cannot see the question.
Yeah, I understand.
Sorry. So yeah, let's continue. So in case of this video, it shows, did you see that the horse becomes very weird? And then it shows very abrupt changes like at here. Because the first chunk and the last chunk do not communicate. And in case of diffusion, while at first a camera is running and then a camera stands still, but it shows very noise-like artifact. But in case of ours, we do not suffer from the kinds of artifact, and we generate a camel running and then stand still. But definitely we do not correct the original artifact of text-to-video diffusion models. Some text-to-video diffusion models suffer from like a camel is run backward, which is not natural, but just when generating a single short sample, it generates like this kind of unnatural motion. So we cannot correct them, but we cannot make wrong videos in that require long range temporal consistency. Yep, so in summary, we focus on tuning-free multi-band long video generation with our framework SynCoS. And SynCoS is a unified sampling framework for multi-band long video generation. So in this paper, we focus on how to extend the existing capability of text-to-diffusion models for generating long videos with diverse dynamics. And our solution is to maintain a shared denoising trajectory across both short and long distance chunks. So you can find more interesting samples in our homepage, which is like object motion control and more cinematic effects and storytelling and more camera control and background changes and like that. So you can feel free to watch more videos in our homepage. So yeah, this is the last of my slide. So if you have any questions, then feel free to ask me.
Yeah, I think for me, the previous slide about the video results, I got kind of confused because I saw with the SynCoS, so it's like this horse, is it the horse or the camel? Okay, the camel. It's sort of like there is semantic incoherence in the video. Like I saw like 4 legs behind the horse, and then where it was moving backwards. And I think I missed the explanation for that. Yeah, if you could highlight for that. And then these other models, the performance of FIFO and Gen L video in this same video. Yeah, so um okay. Okay, so does this mean that SynCoS still remains the best performer out of these two?
Oh, yeah.
Okay. So when I sort of like looked at the video, and why would we say that SynCoS remains the best out of these two? Because it seems also to display, I saw some sort of like incoherences in the video, and sort of the way we expect the camel to be behaving. So my question is, even with such a result, why would we say that SynCoS remains the best out of these two?
The major reason is general video and people diffusion do not care about long-range temporal coherence. They just focus on local smoothing.
Okay.
Yeah,
frames interacting with each other, like connecting to each other.
yeah, they just focus on the connection between all the adjacent chunk, not the long distance chunk. That's why ours show the smooth transition, but also ensure long range temporal coherence compared to
Yeah.
other two previous work.
Okay. Makes sense. Thank you for that.
Hello.
Yes, someone has a question.
Hi, Kim. Thank you for the presentation. I hope you can hear me clearly. My
Yeah, I
Yeah,
can hear you.
sure.
so great. Okay, so I was trying to understand more about the collaborative score distillation because my understanding is that you're using different models and trying to aggregate the result to come up with one good model, right?
No, I used just one model.
You used just one model. So could you kindly explain how exactly collaborative score distillation works? How different is it from the other modes of
Techniques,
yeah.
I think.
Yeah, so basically it just used the one model, but the difference here is, so as shown here, in case of just basic sampling, that it just generates just one sample, like this single patch. But in case of ours, although we use a single model, we divide the long image into the overlapping lots of patches and then impose consistency between them. We
Okay,
care about, yeah.
Okay, you can go ahead.
Oh yeah, so we care about consistency between samples, not the communication between different models.
Okay, so in terms of resources, does this method use up more resources than the other methods because of this?
In terms of resource, as we need to optimize samples, so it requires more training resources, but that is not very significant. At every iteration, we do not need to update all the patches. We just sample from all the patches. We just select the subset of the patches and then update the patches. And then next iteration, we subset the other patches and then update the patches. And the next iteration, we randomly select subset of the patches. So we do not need to update all the patches, so we can save the computation resources.
Okay.
Under
Thanks.
memory constraint. Yeah.
Yeah, thank you.
Okay. I don't know whether there are still other questions. I think complementing on what Emily asked, there is a slide where you were comparing, and I think these techniques, the score distillation, and I think there's another form of distillation that you are comparing on a previous slide, and we looked at those other videos that were being generated. I don't know that. I think it's not this one.
This slide.
I think it's forward.
Forward.
It's quite ahead when you move.
Yeah. This slide.
Next, maybe.
This.
There's a where you drew the graph with the time steps.
Draw with the time steps. Maybe this part.
No. Yes. I think this one. Yeah, this one. Though there was another one with this this. So I think this is where the sort of confusion came from, that you were trying to compare the results of your model and these other two. Yeah. So I think this is where the unclarity came from, but I think it has been cleared, and I want to thank you. I want to thank you, Kim, for the presentation. I don't think other members have questions. I don't see them.
I have one last question.
Okay.
Oh, sure.
Okay, so it's currently text to images or videos. Is there any work being done on image to these high dimensions that you're talking about in your work? Are you looking at instead of text to images, but using images to
video generation,
to videos or higher dimension? Yeah, that's my question.
Yeah, that could be applicable, but I do not explore that. But we can just explore by changing the model to R2V or something else to see the result.
Okay, thanks.
Okay, that looks like there is a research paper that can come out of that. If someone wants to pick it up, to explore how long-range videos can be generated from images, picking up from Kim's work, I think it would be a wonderful work, like wonderful research. So thank you, Kim, once again, and the members for turning up. I want to thank you. Thank you very much. And to the other members, I think we'll meet again in their subsequent sessions. But great thanks to Kim. Thank you for your time and for the wonderful talk.
Yeah, me too. Thanks for everyone and everyone's valuable time. And also, I'm happy to share my work to you guys. So if you have any further questions or something else, then you can send me an email.
Sure.
Thank you.
All right. Regards to Professor Jinsu, your supervisor.
Yeah.
Yeah, so really, thank you very much. And
yeah,
it was great meeting you from KAIST. All right. Bye-bye, everyone. And bye-bye to Kim. See you next time.
Oh, yeah. Thank you. Bye-bye.
Okay.